Hello, welcome back. So today we want to talk about measures of variation and explain what that means and how we calculate them. So our goals, as it says, understand what these measures of variation are, how to find them, and then also understand the properties of the standard deviation, which is the most commonly used or probably the most important measure of variation. First off, let's explain what a measure of variation is, the concept. So it says measure of variation is a number that tells us how spread out the data is. So when we talk about measures of center, that just tells us where the middle of the data is. But now I want to get an idea of how spread out data is. Kind of how far apart, values are, and just kind of some idea of the shape of this distribution. So let's imagine here on the right, let's do an example kind of to motivate this. Let's say you're driving along and you see two cornfields. Okay. Now, let's say both have the same average height. Of the plants, of the corn plants. Okay, so the first one is called field number 1. So here's the average height right here. And let's say the corn, so a lot of these corns from professional fields, they look kind of like this. So the corn, the plants are really close to this average height. Okay, they all have almost exactly the same height. Let's say it looks something like that. Okay, that's field number 1, with the line once again is average height. They're all really, really close to that average height. Now, let's say you come across another field, field number 2. Let's say this is the average height, and let's say looking at it, it looks more like this. So some plants are really high, some are low. This is still the average, but it looks something like this. Okay. Now, they both have the same average height. What we'd say is that field 2 has a lot more variation. There's a lot more variation in the heights of the plants. Okay. So that's the idea of variation. That's what it means. So here, once again, they have the same average, but here the plants are really close to the average. Okay. And here they're a lot more spread out. So looked at a distribution of those. Okay. The distribution might look something um, a lot more like this. So for field 1, it might be a lot like, let me actually change that a bit. Let me actually make it even more pronounced. So it might look something a lot like this. Okay. Where this is the average right in the middle. Okay. And basically all your values are really, really close to that average height, as we saw here. That's what the distribution might look like. Now, over here, if you looked at field 2 distribution, what we'd expect to see there, once again, remember this is height is along this axis, frequency is along this axis. I expect to see here is something looks more like this. So possibly also symmetric, probably, but also a lot more spread out. Okay, so this is the average right here, or the mean height. Okay, a lot more spread out. Okay, and once again, that's because it has a lot more variation in the heights. Okay, once again, over here, they're almost all exactly the same height. So they're all bunched together close to the average. Over here, there's a lot more variation and they're all spread out. So our goal then in measures of variation is to find a number that we can use then to describe that variation. Okay, how much it is. Let's take a look at that. So let's come back over here to the left and talk about the 2 main ones we'll use. The first one, the simplest one to do, is the range. It says the range of a set of data values is the difference between the maximum data value and the minimum data value. It's a single number, and it just gives the difference between those two values. Okay, so that's the simplest one to calculate, but kind of much like we talk about the mid-range in measures of center, it is then sensitive just those maximum minimum values. Okay, if the rest of the data changes, if you have a totally different data set, has lots of values, variation, and different kinds of variation in between those two, looks a lot different, but as long as it has the same minimum maximum value, have the same range. Most important one is the one's called the standard deviation. Okay, this is the measure of how much the data values deviate away from the mean, and basically kind of tells you in a sense how far a data value is from the mean on average. So it's kind of like an average distance from the mean of a data value. Now, depending on whether we have a sample of a data or an entire population, we calculate it slightly differently. They both were based on the same thing except for the denominator. So how the standard deviation works, to start with the sample, and we'll see this in a couple examples. We'll start with, well, first off, I have to find the mean of our data set. That's this. So each x value is each data value. The x with the bar on it is called x bar. That's actually our average value. So what we'll do to find this is we're going to subtract the mean from each data value. Then we're going to square that result, and we're going to add all those up. Remember, this Greek letter here, sigma, means sum. Then we're going to divide by a number, in this case for the sample, n minus 1. And then that, we take the square root of that, that's going to give us what's called the standard deviation, this average distance of a value from the mean. Now, you notice the only difference here has been the notation. So here, the population, the sample mean is called x bar, with the x with the bar over top of it. A population mean is called this Greek letter mu. Okay, and then for a sample standard deviation, we use the letter s. For a population standard deviation, we use the Greek letter sigma, the small lowercase sigma. And then n, small n, is the number of values in our sample. And then for n is the number of values in our population. So the idea of sampling, we'll talk about that quite a bit. Well, that's something we'll talk about more in other statistics ideas. But the idea of often an entire population is too difficult to study. So I want to take like a smaller representative sample. Okay, so maybe your entire population might have millions of values. We just want to take a smaller sample. It's easier to work with, maybe 1,000. And so that's where n is, that's the number of samples. Now, the only difference in between the two from a sample and a population is for a sample, you divide by the number of the sample size, n, small n, minus 1. Or in the population, you just divide by capital N, which is the entire population size. The reason for this is kind of complicated. It's not really necessary to know. What it has to do with is for a small sample, then basically, since we're using the mean, we already have one. That means we essentially have one data value fixed. So we only have what are called n minus 1 degrees of freedom. And also, it turns out in estimating, n minus 1 usually is a better estimator of the actual, is more closer to the actual population standard deviation than if we just use small n. But don't worry about that too much. The main thing is just being able to use them. And also, and make sure if you use statistical packages such as Excel, you understand how to use those and which one to pick. Now, the standard deviation is one we use most of the time. Now, the variance is what happens, is just like the variance of a sample is just s squared, or this without the square root. And a population variance is this without the square root as well, or sigma squared. Okay, so once again, sample variance is small s squared. Population variance is sigma squared. And that also gives you an idea of the variation, but usually in most cases we determine the variance en route to determining the standard deviation. The standard deviation is much more useful. Now, a couple ideas, we're actually looking at some examples. This is a round off rule. It's a good idea to follow. This is rounding the value of a measure of variation, carry one more decimal place than is presented in the original set of data. So what that means is just as it says. So if all your data values are made to the first decimal place, then for the variation, go at least one more decimal place beyond that. And finally, one other concept is called the range rule of thumb. And the range rule of thumb says that for many data sets, your vast majority of your sample values lie within what are called 2 standard deviations of the mean. So therefore, extreme values tend to be more than 2 standard deviations from the mean. Okay, so basically this is just kind of a good rule of thumb that's used to determine what values we think of as being as extreme values, extremely large compared to the population or extremely small compared to the population. And if values are within 2 standard deviations of the mean, either above or below, beyond that rather, then usually they're considered to be extreme. Let's take a look at a couple examples first. Let's look at our definitions again. Let's come over here. So what we're going to do is we want to calculate standard deviation. All right, look at our first example. We could do this, help us using Excel to help us out. This we don't have to actually calculate all these values by hand. We'll do a really small data set. This will also give you an idea of why it's valuable to have programs like Excel to help us do that. So this data set is going to be just 4 numbers. So 20, 25, 27, 30, and 31. Okay. Now the range is easy to find. The range, once again, just the largest minus the smallest. So 31 minus 25, which is 6. So that's kind of like the absolute extent of the range. How far the data values are apart is just at most 6. Now the standard deviation, to help us find that, we're actually going to use Excel to help us do that. So I've already set this up in Excel. I'll also have a few features of Excel. So here are our data values. Once again, that's what we call X. Now, 25, 27, 30, and 31. Now I want to find first we need to find the average of those. So I'm going to do that. So to do that, you need to use the functions in Excel, put an equal sign. And then if I start to type in standard deviations, ST, you can see it comes up. Now here, I'm going to do this as a sample, do both. As both a, I'm sorry, I'm going to get ahead of myself. Let's find the average first. So the average, just AV, the average right here. Double click on that. And then what we can do is we can click on our first value and drag this down. You click drag down. Oops, sorry. Hang on, let's do that again. So AVG, or average, double click on that. So click on the first value and drag down. And what that does, it tells you the range you want to find the average for, from the box A2 to A5. Then we need to close that parenthesis right there and hit enter. That gives us our average. That's the average of those 4 data values. Now, I'm going to put that in right here. This makes it easier to do this spreadsheet. And also, instead of having to do this, enter that by hand for each one, I'm going to click on this. If you click on the little box right here in the corner and drag that down, it fills in the rest of those boxes with that number. Now, why I did that is then to do the next part of the formula. The next part of the formula is we subtracted the mean from each data value. So I'm going to do that over here. What's going to want to do is hit the equal sign, calculate that. And so I'm going to highlight this box, which is that value, minus, just click on this box with that value. If I do that, enter that. Now, if I click on this little box in the lower right-hand corner and drag those down, what it does, it calculates that for each row. Okay, so 25 minus the mean is this number. 27 minus the mean is this number. You can check this on your own. And when you see what we expect to have, so when you subtract this, data values that are less than the mean are negative, gives us negative values. Data values above the mean give us positive values. Okay, now the next part of our formula, we want to square this value. So I'm going to take that, once again, hit an equal sign, click this box, and then raise that to the second power and hit enter. And then once again, click on this little, or put your cursor over that little box in the corner there and drag that down. That will do it for each row. Okay, and once again, these are squares. They're all positive, as it should be. Now, I want to sum those boxes. Okay, so I'm going to put under this column the sum of that. I'm going to do it right over here. It equals, then The way to do that then is just use sum, just use SUM. Start to type it, you'll see it right here. Double click on that. Once again, click on the first value and drag down to your last value. Close the parenthesis there. Hit enter. That's the sum. Now, the standard deviation, we just have to, well, we're almost there, we have to divide. Okay. So here, let's do sum for a sample. Okay, here, let's do this value right here. Let's get hit equals this value divided by n minus 1. In this case, our n is 4. Let's do it for a sample. It's going to be 3. And then the standard deviation. I'll abbreviate that. Just naming it here. Once again, we're going to take the square root of this value. So you can do that is if you start to type in SQRT, and we'll click on that, highlight that value, and that gives you the standard deviation. Okay, so once again, what this value tells you is that on average, each data value is about 2.75 units above or from the mean, either above or below. Okay, once again, our mean is about 28. This tells you about 2.75, about 3 units from the mean on average above or below. That's our sample standard deviation. Just looking for a sample. Okay. Now, let's check from Excel. I'm just going to name these. So I should also show you the function to find the standard deviation from Excel. What we're going to do is once again, it equals, then just type in ST, and then here, notice we did a sample. So there are 2 possibilities, standard deviation, population, and sample. And once again, it does the same thing. So population divides by the total number. A sample divides by n minus 1. Okay. So let's click on that and then drag these values down and get exactly the same thing. Okay. So Excel gives us the same thing we expect to get from that. Okay. Now, so if we go back to our briefly, let's go back to our screen. So let's actually type in some of this, or put in some of this. Okay. So once again, our sample standard deviation. Okay, is going to be once again the our formula S looks like this. So it's the square root of the sum of x minus x bar, which x bar is your mean, squared, divided by n minus 1. Okay, and we found that to be the square root of the sum, which was 22.5 divided by 3. Then we found that to be about 2.75. Okay, now if we do the same thing for a population, it's basically identical, except we just divide. So if this is our entire population, then we'd be dividing the sum and then x minus x bar squared over n, which is the total number. And that then would be the same sum divided by 4. Okay. And we can also do that. So for a population, I'll just do it right here. I'll do it over here, rather. Okay, is going to be the sum I'll do it all together. So SQRT. Okay. Then I can do this number, the sum, divided by 4. Okay, and close the parenthesis. And that sees there is we're dividing it by a larger number. So that then would be about 2.38. Okay. Now, most of the time, your population is not probably going to contain only 4 values. Most times it's going to be a very large population, but that shows the difference in the ways we do this. Now, let's do another example. This is call this number 1. Let's do a number 2. I'm going to make it basically identical, except I'm going to change one value. I'm going to make my first value instead of 21, I'm going to make it 2. Okay, so 2, 27, 30, and 31. Okay. Now, based on what you know about measures of center, what do you think would happen? Well, the standard deviation is based on the mean, so it's also sensitive to outlier. And this 2 acts as an outlier. So if we calculate this, in fact, let's do another sheet and do this. Let me put in these data values. We won't go through the whole process. I'll just do this with Excel. So let's make this 2, 27, 30, and 31. Now, what we expect to happen is go back and look at our values. Remember, I just replaced 25 here with the number 2. What happens is that I have now more variations. First off, look at my range. My range is much larger. You can also calculate range with Excel, but it's easy to do here. So be the highest value, 31, minus the lowest value, which is 2, which is going to be 29. That is a lot larger. Okay. Now then, the sample standard deviation. Let's do that and use Excel. Let's do that over here. So I'll just go straight to that. So the sample standard deviation, I'll just do it below, is going to be, so type in ST, make sure you pick the one for the sample, stdv.s. Okay. The same way, click on your first value, drag to the bottom. As we see, we expect this to be larger. Let's see how much larger it is. It's quite a bit larger, about 13.77. Okay, that's a lot larger. So if we compare those, once again, we can see that the standard deviation is also sensitive to outliers. Okay. Okay, because this data is a lot different than the rest of them. We have a much larger variation just because of this value. And so the mean, your average, is pulled down by this as an outlier. And so since your standard deviation is based on the mean, then the standard deviation is also sensitive to outliers. So here, with our value, this first value being 25, our standard deviation for a sample is 2.75. Here, replacing that first number with 2 makes about 13. So you see the effect of outliers. And once again, that's that effect they can have. Now, let's talk about some of the important properties of, wrap up with this, the important properties of the standard deviation. So what it says, let's go over these. Standard deviation is a measure of how much the data values deviate from the mean. We've seen that. Okay. It kind of gives you an idea of, on average, how far our data value is from the mean. Standard deviation is never negative. That's because we squared all the, because in our formula, let's go back and look at our formula here. Okay. We take data value, subtract the mean from it, and square it. So it can never be negative. Okay. The only possibilities are for it to be positive or 0. The only way it could be 0, it says it's only 0 when all the data values are exactly the same. So if we had a population with all the data values being exactly the same, your standard deviation would be 0, and that makes sense. In that case, there'd be no variation at all. Okay, large values of the standard deviation indicate greater amounts of variation. That can either happen because of an outlier like we saw, or just more variation in the data. Now, one of the most useful things about the standard deviation compared to the variance is that the standard deviation, actually skip one, which already said, the standard deviation can increase dramatically with the one or more outliers. We've seen that. Also, the units of the standard deviation are the same as the data values. So for example, if these were heights of something, okay, or weights or something like that, say these are in pounds, then our standard deviation is the same units in pounds, okay? Now this next bullet point, I'll mention it, this is not something is important at the moment. And the sample standard deviation S is a biased estimator of the population standard deviation sigma, which means that values of the sample standard deviation do not center around the value of the population standard deviation. Now, when you get into what's called inferential statistics, that's a bit of a problem, but here we're not focused on that. And one more thing, the variance, or the square of your standard deviation, has the same properties, except the units are squared of the original values. And the variance is not as useful because it's a much larger number. It's a little harder to gauge what it means, okay? Because as a square, things increase much faster with a square, and so it's a little harder to kind of understand that, okay? And that the sample variance is an unbiased estimator of the population variance. So that's one reason why the variance is useful. It's in the future, we may talk about biased versus unbiased estimators, but not today. But variance is an unbiased estimator, which is preferable. So here, we didn't write down the variances. For example, the variance of this would be the square of that. And I guess we can even do that really quickly. So the variance, let's just make a little here. So the variance, let's do it for the sample, S squared. Let's square that. So 2.75 times 2.75, that's about 7.56. Okay. Now, the thing is, this square doesn't really have the same meaning. The units would be squared units. Well, once again, if these are in weights, for example, 2.75 in pounds, this would also be in pounds. This would be in pounds squared. It's harder to interpret, and also it doesn't give you the same feel for what this means. Especially down here for this example, it's even worse. 13.77 squared. Okay, we can calculate that quickly. So S squared, 13.77 times 13.77. Yeah, that's a very large number, 189.61. You can see it's not as meaningful. That's why you like to use the standard deviation. So what we've learned today are basically the basic measures of variation, which the ones we'll see the most are the range and the standard deviation, also the variance. So our goal is to understand these measures of variation, how to find them. We did that. And also understand the properties of the standard deviation. We discussed those. So have a good day.